presentation. I'm really happy to have the opportunity to be here in Hamburg and to present some work. So I'll be talking to you about balloon observations. I do want to take the opportunity to mention one little thing first. It came to mind that, so some of you may know by name Vladimir Zeitlin. He was a colleague, and in fact, he was my PhD supervisor back a few years ago. He passed away last June, and we'll have a symposium, GFD symposium, in May in Paris in his memory. And if anyone's interested in GFD, it doesn't have to be on work related to Vladimir, who contributed a lot to understanding almost everything with shallow water models. That's the title of his book on GFD. So if you're interested, save the date and contact me if needed. So what I want to talk to you about today is what we can learn about gravity waves from balloon observations. And that may be a bit mysterious for now, and I hope by the end of the talk, the curves will make more sense. And I just want to acknowledge that this is work that's been carried out with a number of collaborators I'll mention as I go along the way. I'll try to be brief regarding the introduction. The main frame in which we're interested in gravity waves the main motivation comes from modeling and the impact that gravity waves will have on the middle atmosphere. And I've taken this figure from a review that's been coordinated by Ulrike Hatz and a number of collaborators. And it's their first figure. I don't want to go through the details of the figure, which is a little bit complicated and has a lot of information in it. It's describing how the different scales interact at different altitudes. And we can think of this as MF is for the mean flow. Here we have more planetary scale activities, down to synoptic scale, and here the small scales and gravity waves. And the one thing to note is in the tropospheric heights, you have the arrows going just this way with the large scale flow impacting how the gravity waves may develop. And that kind of explains why in dynamic meteorology courses in teaching, when you explain the basics of the tropospheric circulation, you do that with a quasi-geostrophic model, where you can filter out the gravity waves because they're unimportant. And so you get educated thinking, well, gravity waves are unimportant. We can just understand everything, filtering them out. But at the other altitudes and in the middle atmosphere, you see the arrows are going both ways, with the gravity waves contributing to the shape of the flow, which itself influences them. And of course, as they're rather small scale processes, they are generally unresolved. And so in the models, they'll be parameterized. And so this is not a sketch from a paper, it's a made up sketch, just a schematic. The way we tend to think about motions in the atmosphere and in models, you can imagine that the blue curve describes reality or some observation of reality. And we know that models will only resolve part of that, so that the remainder needs to be parameterized. That's the simple sketch we have, of course. And there would be things to say on that. Gravity waves needing to be parameterized for the way they force the background flow in the stratosphere and mesosphere. The main thing we want them to do is to propagate up in a way that depends on the background flow, dissipate in a way that depends on where they meet critical levels. And in the frame of gravity wave parameterizations that has been set up starting from the 80s, the general way of thinking and doing these things is that one has sources, which ideally can be connected to orography, convection, jets and fronts. And then the propagation will be, well, it's constrained to be in each column. It's columnar, and it's based on well-established physical approximations like WKB. So there's not much to do about the propagation. We rather trust it. It's just it's constrained to be columnar. And people have found that in the dissipation and forcing, of course, there's various ways you can do that, but the critical thing is that it takes into account critical levels, so that when tuning the parameterizations, because of course there's parameters in there, and at one point you need to determine them, and they're probably constrained. When tuning, you're mostly acting on the sources. At what height do you say that there's gravity waves that are launched? What are their amplitudes? And the amplitudes will be typically quantified in terms of momentum fluxes, because that's what will be important for the forcing. And perhaps you have some characteristics of the waves like phase speeds that you need to determine. And there's this little phase because, well, we're generally unhappy with what we have as information and constraints on the way we tune the parameterizations. But because of this frame, and because the way the parameterizations are set up, there's been over the past decade or 2 decades, a strong emphasis on better quantifying sources of gravity waves. And that's difficult because they're small scale. And so a key thing is to find reliable observations to describe them. And so that comes to the third point of my introduction, the need for better observations of the source of gravity waves. And there's a lot of information, and I won't go into that, from satellites which have the advantage of being global and giving a global picture of what's happening, but they have limited resolution. And in situ observations can have the advantage of giving more reliable, more accurate information, but they are extremely sparse. They can give information about small scales, but they're extremely sparse. So that's where the balloons come in. And I'll have the following outline for the talk. I'll talk a bit about the balloon campaigns, the Strateole 2 project. I'll talk about gravity waves observed during Strateole 2. And then I'll go into some other topics like what we can do using machine learning and those observations. And that will bring us to a discussion on how do we move forward and what do we really want to know or achieve. And so we've done the introduction and we're at this point. So I'll take a little time to tell you about balloons because they're fun. LMD was founded more than 50 years ago, Laboratoire de Météorologie Lab. And there were essentially 2 pillars for LMD. One of them is modeling, of course, and the other was observations. And at the time, there were very few observations of winds in the southern hemisphere. And so it was one of the big projects, was called Ecole, and it consisted of sending balloons in the Indian Ocean. So the map here, you can see the southern part of India and the northern part of Madagascar, and balloons were launched to get some idea of what the winds were over the Indian Ocean. At first, the balloons had their equipment and measurements and sensors below, and they realized that when the balloon, which were flying in the boundary layer, came to the sea and then back up, when they came back up, the instruments were dead. So they had the idea of putting the instruments inside, and it contributed to things. So that was the 60s, 70s, beginning of the 80s. I won't give you the whole history. In short, that's normal. When I want to make sure I have the audience attention, I do that. So in the 80s, 85, the people realized there was an ozone hole. They realized it was really interesting and important to better understand the dynamics of the southern polar vortex. And then came the idea, well, those balloons which we've been flying in the troposphere, you saw the balloons there, they were a few meters in diameter. Let's make them bigger and fly them in the stratosphere. And hence we had this big, after Ecole, during which they launched 500 balloons. So it's a huge number of balloons. They started thinking about Strateole, and it took quite a few years to develop the balloons, have them able to fly for long duration in the stratosphere. The good thing about flying balloons in the stratosphere is that there won't be any convection disturbing them there. They can fly for a long time. And the first campaigns were then in 2005 around Antarctica. And so there were 2 big campaigns, 2005 and 2010, Vorkor and Concordisi. And during the 2010 campaign, to make sure everything worked, they had a pre-campaign, a technological campaign, where they launched balloons from Seychelles in the Indian Ocean, just 3 balloons. And that was the pre-Concordisi campaign. The balloons flew at 18 or 20 kilometers, and we realized they were giving a lot of very informative information on winds, on motions, on waves in particular. So this is just to make the balloon's a bit more concrete. That's launching from McMurdo in Antarctica from the 2005 or 2010 campaign. And that covered a lot of the Antarctica and Southern Ocean. And the balloons, I want to emphasize that, they have an inextensible envelope. And we fill them with helium with a bit of a superpressure relative to the flight level at which they will drift. So their volume is fixed. And since the instruments don't change, their mass is fixed. So they're constant density objects. So they just drift with the wind as an isopycnic object. And that's fantastic because isopycnic is not very far from isentropic. You can correct for that. And so you have a quasi-Lagrangian behavior. So you're following a fluid parcel. And that's really informative. It's not the usual way we think about the flow, but it does give you interesting information, especially for waves, because it gives you the intrinsic frequency of the motions you're observing. And you know that the intrinsic frequency tells you if you're in the mid-latitudes or high latitudes between F and Brent Weisela, what you're observing is a gravity wave, and you can tell exactly what its intrinsic frequency is. So these are spectra that were obtained by Aurélien Podbegène from the balloons of Concordia Z. You can recognize the peak close to the inertial frequency. You have the potential energy in red, kinetic energy, horizontal kinetic energy in blue. In green, you have the vertical kinetic energy. You see that the vertical velocity is a dirty field with a flat spectrum, and there's going to be plenty of vertical velocities at small scale, as you know. You see that from the pre-Concordia Z balloons, there were just 2.3 balloons. That's because one of the balloons flew out to the mid-latitudes. There are 3 balloons. And so it's noisier, but you recognize the same kind of spectra. You don't have the inertial peak because there's no inertial cutoff. And you do note one little thing, there's a bump here. And so some of you may say, hey, what's that interesting bump at the Brent Weisela frequency? What's happening? And that is an interesting bump, but it is not possible to exploit it because the signal at those frequencies is polluted by the balloon's own oscillations. You put an object in a stratified medium. Whenever you perturb it, it just oscillates around its equilibrium position. These oscillations happen with a period which is 3 minutes. It's a little bit shorter than the 5 minutes of the stratospheric Brent Weisela period, but it's just too close. And so whenever we look at the gravity waves, we look up to periods as short as 15 minutes. We could go to 10 minutes, but we won't go down to 5 minutes. Just to say, if anyone's interested in observing gravity waves, superpressure balloons would be an excellent platform. And so, in addition, as you could guess from this, here there were just 19 balloons flown. Once they're up there, they have solar panels. They drift for 2 to 3 months. They cover a wide area. So they have a great spatial coverage. And we're not giving them any fuel or anything during that time. And so the following years were spent preparing new campaigns in the tropics. And that's why the project is called Strateole 2. Again, it's stratosphere, and it's the tropical equatorial counterpart of the Antarctic campaigns. I want to acknowledge that the coordinator is Albert Hertzog, who you can see here, and that's what the launch of one balloon looks like from the airport of the Seychelles in the Indian Ocean, where we launched them from. So, why are we doing this? I come to motivations and scientific objectives. So I'll set out 3 or 4 major objectives. The first motivation is to better understand the dynamics. And in particular, in the equatorial region, there's a lot of question about determining, well, what the different families of waves, equatorial waves, from the large scale down to the gravity waves are doing. and to quantify their contributions to the QBO. I've taken this figure from the paper by Richter et al. Of the QBO initiative, where they compare how the QBO is modeled in different climate models and how it evolves in experiments where you double or quadruple CO2. Many climate models now have a QBO that's internally generated, which is great. It has been obtained at the price often of increasing the vertical resolution and making sure the gravity wave parameterization, which comes to provide the additional necessary forcing that is not provided by the resolved waves, is what is needed to have a QBO with reasonable characteristics for nowadays climate. But then when you run the model forward in time with a changing, or you double the CO2 or quadruple the CO2, that changes many things in the model, and the different models give you very different answers regarding what could happen to the QBO in terms of period, amplitude, and that's due to the uncertainties in the forcing of the QBO. You can get a right QBO apparently with different contributions, not for the right reasons in current climate. So that's the first major motivation, and that's mostly what I'll be talking about. Another motivation is that this region in which we fly the balloons, around 18 to 20 kilometer height in the equatorial band, that's the lower stratosphere just above the top of the tropical tropopause layer. And that's a crucial region because that's where the air enters the stratosphere. The world Dobson circulation is such that the air enters the stratosphere there. So the composition, the characteristics of the air entering the stratosphere is set by the processes which happen in that region. And these are processes happening on a wide range of scales, from the planetary scales for the QBO, somewhat shorter scales for, say, Kelvin waves, down to gravity waves for the shorter scales and turbulence. And there are some processes, for instance, cirrus clouds, which are important in setting. So we see a cirrus cloud in this sketch from the paper by Jensen and Randall in 2017. The cirrus that form in situ will have a formation which will be very sensitive in a very nonlinear way to the temperature fluctuations. The temperature fluctuations will be driven by wide array of motions, and the short-scale gravity waves will be contributing rather large, fast temperature variations. Do these influence how much the air is freeze-dried, how much water goes to the crystal phase which sediment out? That's still unclear. And that's some of the topics that we want to investigate in terms of composition, water vapor, particles, and cirrus clouds. But I won't be talking about that today. And then there's just knowing what the winds are. The winds are really poorly constrained in the tropical lower stratosphere. Geostrophic balance doesn't apply, and we don't observe the winds except for Aries. There's just very few weather stations along the equator. It's 40,000 kilometers around. And so from the few radiosondes that we have, we don't have a lot of constraints. This is illustrated in the paper of 2014, which motivated the ALS mission, where what is represented is the agreement or disagreement between different reanalysis. So you see that at 300 hectopascal, comparing ECMWF and GFS, and you see that there's the major peaks of disagreement between the reanalysis and the equatorial ocean, especially over the Pacific and over the Indian Ocean. And so the observations of the low stratospheric winds from the balloons have been instrumental in doing calibration, validation, comparison with the ALS measurements and in providing information about what the different models and reanalysis are doing in that region more generally. So within the Strateole 2 project consists of 3 campaigns. We've done 2 of them. a first technological campaign in 2019, where we launched 8 balloons and they flew for in total something like 60, 80 days in total. So an average flight of 84 days, and they cover the whole equatorial band. Relative to the coverage of previous campaigns providing in situ measurements. So previous campaigns providing in situ measurements in the tropical low stratosphere would be airborne, like the Atrix campaign in 2011 to 2014, and they were just rather localized. So here we have a data set which covers the whole equatorial band. There were some issues with the balloon envelopes in 2021. So although we launched more balloons, some of them failed and we have a shorter average flights. And the next campaign, due to those balloon envelope issues which have had to be examined and resolved, will be in 2026. I'm not going to go into the details of the instruments. This is to say that not all the balloons fly with all the instruments. There's a large set of instruments measuring things from, well, of course, temperature, ozone, CH4, CO2, particles. There's a backscattering LiDAR looking down, and there's different configurations of balloons which fly at 18 or 20 kilometers with combinations of the instruments that make as much sense as possible. And all the data sets are made publicly available about 1 year after the campaign. So if anyone's interested, it's all available and you can ask us. If there's any questions, I didn't say at the beginning. Okay, so now you know it's safe. Don't hesitate to interrupt. Okay, so what did we observe in terms of gravity waves from this first campaign? This is work that was done by Milena Korkos, who was doing her PhD and is now in Boulder. And well, the basic idea is, as I said, the balloons give us measurements that are Lagrangian or quasi-Lagrangian. And the good thing also is that they give us measurements of several variables. We have the pressure, we have the velocity. And a funny one is temperature. You'd think we should have temperature. And we do have temperature. We even have 2 temperature sensors. But I found it funny to realize that the temperature measurement is not that great because it's difficult to measure because there's not much air out there at 20-kilometer height. And the balloons are drifting with the wind. So there's not much wind providing heat exchange with the temperature sensor. So temperature happens to be a difficult measurement and it's rather noisy, so we don't use it. But just to highlight that that was not fully intuitive. Having those and having access to the intrinsic frequency using polarization from linear wave theory and isolating wave packets from a wavelet analysis of the time series, we can calculate momentum fluxes, and these are considered rather accurate estimates of the momentum fluxes relative to measurements that one can have from, say, satellite observations, which will have only access, for instance, to the temperature perturbations, and then rely a lot on inferred quantities from linear wave theory. Okay, so that's what I meant to say on that topic. So let's look at an example first. This is an example of a case which was chosen because it corresponds to the most intense momentum fluxes observed. This is to situate, so we are following one balloon in the Pacific Ocean, east of Indonesia, and we'll be looking at zooms. So that picture was just to understand where this is located on Earth. The colors correspond to OLR from geostationary satellites to give us an idea of where the convection is happening, with the bluer colors corresponding to colder brightness temperature, so the clouds that are reaching the highest levels. And if we now look more closely at that kind of situation? Well, naively, the kind of sketches we have about how convection generates gravity waves comes from either idealized theoretical modeling, where you can specify a heating source in a region, and then if you have a fluid at rest above, you have a cone of waves emanating from that. And there's been numerical simulations describing that. And naively, one would think that there's plenty of waves around such a region. But one also realizes that the convection below is much more complex than the simple isolated convective cell considered in either the idealized calculation or the idealized simulation I was vaguely sketching. This is an example of what the velocity measurements look like for that time, for that case. And unfortunately, here I have to mention one limitation, technical limitation of the balloons. When it happens that the balloon flies over a really high cloud, there's little infrared radiation going up. And so the helium in the balloon tends to cool. As it cools, it contracts, and it can contract sufficiently that there's no longer a superpressure. So instead of staying spherical, the balloon starts to decrease its volume. So the object descends by a few hundred meters. When that happens, there's depressurization. It no longer behaves a quasi-Lagrangian way, and so we can't exploit it anymore to calculate the momentum fluxes. So it was going above a really tall cloud, pictures, and by eye also, I take the advantage of this graph to highlight that there's a lot of small scale stuff happening, and it doesn't really stick out necessarily evidently that, oh, at this point or at this point, there's a nice nearly sinusoidal wave packet occurring. Although you may spot that during that time, there are quite significant oscillations in the meridional velocity and in the zonal velocity, with peak-to-peak variations of more than 10 meters per second. Yeah, 10 meters per second over just a few, short time scales. So if we look at succession of graphs like this, these times correspond to when there was the depressurization, and indeed the balloon was above the tallest part of the cloud. The point I want to highlight here is that visually, we don't see anything that would suggest that there's more, there's a situation better suited for observation of gravity waves at a specific time than another. It's just always in the vicinity of very active convection. And I'll also mention that a bit later, we will be trying to quantify how close the balloons were to convection, and we'll be using such OLR fields and finding the location of the nearest location where the brightness temperature goes below 235 Kelvin. So if we now look at the time series of the momentum flux, yes?
Maybe a stupid question from the atmosphere. Where does the data from the map come from? Because you don't have balloons everywhere, right?
Where does the data from?
Data that we see in the map.
So the map comes from geostationary satellites like Himawari or the
measure them in any height, or
no, they give us the brightness temperature. So they give us the height of an estimate of the height of the top of the clouds.
Okay.
And that's why it's just a 2D field, and the color bar has been chosen to indicate where there's convection, and the bluer colors indicate cloud tops that are really reaching.
Okay, thank you.
No, good, thanks. So if we look at the time series for the momentum fluxes, the horizontal scale is time, and it only covers about 2 days. And the vertical scale is momentum fluxes in millipascal. Over the whole campaign, the mean momentum fluxes observed by the balloons and attributed to gravity waves is about 5 millipascal. That gives you an order of magnitude. And we also calculated that this 5 millipascal is a significant forcing. It can be contributing 25% to half of the forcing needed for the QBO. That's a significant number. I'm saying this to give some context. When we look at the vertical axis here, which goes from 0 to 120 millipascal. And so in this case, we have a configuration at during a few hours such that the momentum fluxes associated to the strong peak-to-peak oscillations I was highlighting just before reach 120 millipascal. So it's a huge value. It's the largest, in fact, during the campaign, but it's to emphasize the very intermittent, very local character of the waves. And I've taken time to highlight the relationship to the convection to emphasize that it's not straightforward at all. And then it's more the convective field is much more complex than the simple pictures we have from idealized studies on that. So what can we do with these measurements? Well, we can try and describe the distributions. I've given you already the mean momentum fluxes. We can describe the intermittency, and I'll talk a little bit about that. We can describe the spatial distribution. I won't talk about that. I think we have done it. We have made maps of the whole equatorial band of where the momentum fluxes are larger. I tend to think that's not necessarily the most useful information because the maps tell us, well, the momentum fluxes are larger where there's been more convection. And indeed, it just corresponds to where there's the more convection, say over Indonesia. But we can try to relate the momentum fluxes to the flow, and that's probably more useful because that's really pointing directly not to geographical distribution, but to what's happening in terms of the dynamics. And so I'll talk about that too. So first, I talk a little bit about the intermittency. And I want to illustrate that with a time series again. So that's for one of the balloons, the balloon that we were looking at just now. The first time series gives us the variance of the temperature fluctuations. So if we follow the balloon, what's the variance of temperature? So why am I interested in the T prime fluctuations of temperature? Well, because as I've highlighted for the microphysics, there's processes like the formation nucleation of ice crystals, which is very sensitive to temperature and rate of temperature change. So what temperature fluctuations are experienced by a Lagrangian parcel is an interesting quantity for microphysics and the formation of cirrus clouds. There's two curves on that first graph, one corresponding to the whole spectrum of gravity waves. So we're taking periods between 15 minutes and 1 day. That's the blue curve. And a red curve for periods that are what I call high frequency, periods between 15 minutes and 1 hour. And you do see that when you take the whole spectrum of waves, well, it's a signal that varies, but it's not a huge intermittency. When you just take the high frequency, the red curve, it starts to be much more intermittent. This is vertical velocity, very noisy, as you would expect. The insert is just to focus on lower values, so you can get a feel for how it varies. I'd rather comment the last one, which is the total momentum flux. And because of the strong intermittency of the vertical when we saw the spectrum was flat, for the momentum flux, you get time series, which are really very intermittent in the sense that there's fluctuations and then there's peaks that are very short and really intense and stick out of the extreme rare events in terms of momentum fluxes. Yes?
A question, do you really measure vertical wind? Because in previous slides you didn't mention this, you said only zonal and meridional velocity.
Yes, that's an estimate of the vertical wind from the displacement of the balloon. And so the balloon is isopycnic, but we can, knowing the displacement of an isopycnic parcel, we can estimate the vertical velocity related to the isentropic displacements, and that's an estimation. And it's fine for the frequencies we consider. When we come down to periods shorter than 15 minutes, the behavior of the balloon itself as an object within the fluid has to be considered. But for periods longer, that's fine. And so another way to quantify intermittency is to plot out the PDF of the momentum fluxes. And that's something that we've been doing quite a lot. But when you do that, you need to do it with if you're interested in the rare events, with the logarithmic axis and the vertical, so that if we were not doing this with the vertical axis, you just have a peak at really short values. The mean is indicated by the dashed curves around a few millipascal. And if you look at with the vertical logarithmic axis in the vertical, you do highlight the really rare but very intense events. And this graph contrasts the PDF for the momentum fluxes close to convection. So that's observed less than 200 kilometers from convection, and far from convection, that's more than 500 kilometers from convection. And so here I'm testing you. I didn't say which is which. So which is which? So the blue curve, which has intense events, corresponds to the balloons close to the convection. And that's really very sharp difference with the balloons that were taken far from convection. That being said, and I'm not showing the graph, we can also plot how frequently were the balloons close to convection. And there's convection a little bit everywhere, most of the time. So the balloons were very often in that category. Such that, okay, it's informative to know that you're close to convection. It changes the PDF of the momentum fluxes, but it's not at all a systematic. It doesn't mean that there'll be important momentum fluxes. And we saw with the case study, you can have a really active convective field, and it does not correspond on the time scale on which the convection is developing on continuous large values of the momentum fluxes. So if we come back to trying to relate the gravity waves to the flow, we can take our measurements and plot them as a function of distance to convection. We've estimated the distance to convection from the maps of OLR, identifying pixels with temperatures lower than 235 K as cloud tops. We've tested the sensitivity to this threshold, it's not important. And we here plot the momentum fluxes for high frequency waves and above for the whole frequency for all the waves. You see a clear sensitivity to how far we're from convection. You see that even when we're close to convection, okay, there's larger values. The dot is the mean, the blue crosses are the median. So there's a clear sensitivity to that, but there's also a huge variability. Another point to note that's interesting is that for the high frequency waves, when you're far from convection, you tend to decrease decay, not to zero, but to really weak values, whereas you decay to a background value, a mean value for when you consider the whole frequency. And that's also consistent with the important horizontal propagation of the lower frequency waves, which means they'll be much less sensitive to how close they can be to sources. Am I losing many of you? Okay. So that's more or less what I've the results I've chosen to pick out on the observations of gravity waves from balloons. I'd like now to move on to questions on, okay, how can these observations be useful? So one could wonder, can they be useful for case studies? And that's a tricky question, because if you want to do a case study, say you could, the case study I've highlighted, you could say, I want to simulate that with a high resolution model, and then I'll compare. But in the high resolution simulation, the convection won't happen in the same way, in the same place, not exactly. There'll be plenty of questions to get the convection comparable to the real convection. And then the comparison of the phenomenon that's been excited by the convection, the gravity waves, will be very dependent on that. And that makes any such comparison rather difficult. We can use it for statistical comparisons. And that's what we've tried in giving a relationship between the momentum fluxes of the waves and the flow, trying to give some relationship relative to the flow, and then people can test if their parameterization does something similar. It can give a constraint that is, we hope, more informative than geographical information. It can be a reference data set for comparisons to parameterized momentum fluxes. And I won't talk about that, but I do want to say how admirative I am of my colleague François Lotte, who has done that. He has collected parameterizations from models, many models involved in the QBO initiative, and he has collected the fields describing the background flow from RF5 all along the balloon tracks. From the fields describing the large-scale flow and the parameterizations, you can estimate parameterized momentum fluxes and compare to the balloons. And we've decided to use that data set he prepared and to use those observations as target data set for machine learning approaches. And so that's what I want to talk about a little bit in the time I've left. How much time do I have?
45 minutes. It's less than 2 minutes, but
so 2 minutes.
Some notes. You have 7.
Okay. So I'll say a few words about that. So I do just want to make clear, what's our purpose? Is it to design a new parameterization? No. The purpose is really to explore the relationship between the large-scale flow and the unresolved process. In any parameterization, there's this idea that knowing the large-scale flow, we can infer what's happening with the unresolved processes. This is a data set to test this question in practice. So the framework we have RF5 providing information on the large-scale flow. We have collaboration with colleagues in mathematics, applied mathematics labs, helping us with the tree-based methods. And our target is the balloon time series of momentum fluxes. And so the kind of question we're interested in is, how much do you think we can reconstruct? Can we say that there's some part of the signal that unresolved process that's stochastic anyhow, and we won't be able to reconstruct it, even if it's just a lower bound on that? And we're also curious to know how much have they learned. You know that the machine learning part is not a black box here, it's tree-based methods. I've chosen brown, but there's ways to interrogate the tree-based methods. This is the input information, RF5, winds, temperature, in a local profile below the balloons. But we also add precipitation, and that's precipitation in the vicinity. That's what is represented by the little squares around each balloon position. We've done that because the precipitation indicative of convection will be a really small scale field, and we think it's not necessarily indicative what is happening exactly at the grid point, but rather what's happening in the vicinity. And so how much can you reconstruct? That's the first question. And this is an example for one of the balloons. We've learned with 7 of the balloons. We're testing on the 7th of the 8th one. The black curve is the observed gravity wave momentum flux. The colored curves are the machine learning reconstructions. And it's rather encouraging, but there's events like here where you clearly do not have the peaks. The correlations get up to 0.7, and the method doesn't count. Our colleagues tried different things. The different methods that they tried, which were all tree-based methods, did not make a significant difference. There's not one which sticks out as hey, this is better than the others. This is just to further illustrate that the peaks are underestimated. And you can say, well, wait a minute, why is it just showing balloon 2? How is it doing for the other balloons? And so indeed, I've biased the presentation. I've chosen the best result. Okay. So this is balloon 2. This corresponds to the 3 methods. Correlation of 0.7. This corresponds to the LMDZ parameterization, which is doing well too. So it's a case which was favorable. And I'm now going to show the other balloons. And so when you look at the other balloons, things to see is that there's little sensitivity to the method. The 3 methods every time are doing similar. There's a lot of variability from one balloon to another. So it's not stable. We're really dependent on the data and we lack data. And so it will depend on and that's consistent with the fact that it's intermittent. You saw that in one balloon flight, you just have a few events. And so it's not going to be stable yet. And we're performing better than the parameterization, which is a bit, which feels, well, okay, that's a check. We expected we were doing that. And another question is, how have you learned? How has the model learned? And interestingly, it learns from the variables you expect, precipitation, but it also learns from balloon level wind. The wind at the local position of the balloon is really very informative. And the last thing that's rather a bit mysterious is that the different methods don't learn, they perform similarly, but they're not finding the information in the same place. And that, okay, let's leave it mysterious. We've moved on to a more probabilistic setting. That is, instead of trying to predict one value for a given situation, to predict a range of values, a PDF, and that's much better. So it's like a probabilistic, a stochastic parameterization. It makes a lot more sense. There's a lot of questions. Knowing the large scale flow, there's not one unique answer, and there's sampling issues regarding what the balloon is observing. And so we found that that's a better setting for this exercise. I'll skip that part. I've been too ambitious on what I want to say. And I come to the conclusions. So I've talked about the balloon campaigns, what we've learned from the observations. I do want to say just a word on this part, how to move forward. I think there's a lot of questions about, well, using machine learning. I've hinted a few things on that, but there's a lot of activity on that, using machine learning from parameterizations. What data sets to use and to trust is really complicated. What you then implement in a model that has a lot of other parameterizations and processes resolved is complicated. And I think there's room for, well, making progress, combining a number of approaches. And among those, coming back to idealized simulations in which you can have a good knowledge of both what is happening, what's the right answer, and what different modeling tools or simplifications or parameterizations or machine learning tools tell you is important and informative. And so that little picture and the part I skipped is that we're trying to explore a simple model for the QBO that's intermediate between the 1D model and full GCM, in which we would have just a 2-dimensional QBO with resolved waves so that we can know exactly what's happening and test if the idealized sketches we have from theory make sense with what's really happening, and if the sensitivity that's observed in GCMs are consistent with what's really happening. And with that, I thank you for your attention, and I'm sorry I've been a little bit over time.
Thank you.